Okay, chapter 2, allocation problems. And this is the first chapter that is AS, so it's probable this is the first thing that you're looking at with me if you're just starting off with decision 2. Now, this chapter, allocation problems, if you have done transportation problems, it feels kind of similar in the sense of like the similar kind of goals. And this writing that I've got here, if you do transportation problems afterwards, you'll go like, oh yeah, I see some of these parallels here. Anyway, in this chapter, we're going to aim to most efficiently, and when I say efficient, I mean by time or by cost, to allocate workers to tasks given the following. First of all, we know how long it takes for each worker to complete a task, or how much it costs to allocate a worker to a task. The other thing that we know is that one worker can only do one task. We need the same number of workers as tasks, so it needs to be an n by n matrix that we've got here. And this matrix that I'm talking about is called a cost matrix because it tells us the cost of how long it takes for each of these workers to perform a particular task. And because there are 4 workers, we need 4 tasks, so there's this 1-to-1 allocation that we've got here. So this is kind of the motivation for this problem, that we've got these 4 swimmers here, and in a swimming relay race, 4 swimmers each swim a different swimming stroke as part of a team. There's the butterfly, backstroke, breaststroke, and front crawl. And given this cost matrix of the times taken for each swimmer to complete one length with each stroke, how should the captain allocate the swimmers? So they need to try and say, okay, well, Adam's going to do backstroke, Boris will do butterfly, Carl will do breaststroke, and Dean will do front crawl. They need to try and allocate these 4 people, these 4 different strokes, obviously to try and get the minimum total time that should be taken because they want to win the race, don't they? So this is what we're going to talk about throughout this chapter. To begin with, we'll learn about the Hungarian algorithm, and then basically the rest is just about manipulating and sort of adapting the Hungarian algorithm. We'll talk about using a dummy, maximum allocation rather than this one, which is a minimum allocation, managing incomplete data, maybe where one particular person here doesn't know how to do the front crawl, which would be a completely mad situation, but you can see how it could come up. And then the last part, which is only for A2, is linear programming. So you'll only need that when you're doing an A2 exam in Decision 2. So let's actually have a look at what the Hungarian algorithm is. It might seem a bit overwhelming at first, but once you try a couple of examples, you'll just be like, okay, cool, this just seems to make sense. So the Hungarian algorithm is as follows. First of all, you reduce the rows by subtracting the minimum value from each element in that row. What this will do is this will create at least 1 0. This will create at least 1 0 in that row because obviously you're going to subtract the minimum value from all of them. So if you're subtracting it from itself, you're going to get a 0. Now you're going to reduce the columns by subtracting the minimum value from each element in that row. And again, that's going to be creating some zeros as well, if there is any. And this one doesn't always have to be done. If there's 0 in each, if there is already a 0 in each column, then that is going to, you're subtracting 0, so it's not going to change anything. Then what you do is you determine the minimum number of horizontal and vertical lines required to cover the zeros in the matrix. If this is n, then you have an optimal solution. If this is smaller than n, you have to find the smallest uncovered element, which we call E. And then step 5 is called augmenting the matrix by E. What you do is you increase any element that is covered by 2 lines by E, because they might be covered by a vertical and a horizontal line, so the one that's underneath is covered twice. Any element that is covered just by 1 line stays the same, and any element, meaning a number in the matrix that is uncovered, it gets decreased by E, probably creating some more zeros. And then what you do is you repeat steps 3 to 5 until the zeros can be covered in n lines. As soon as it can be covered in n lines, then we have, we have an optimal solution, and we can figure out which person should be doing what. So let me just get rid of all of this stuff so that we have this as quite a neat page of our Hungarian algorithm. We're just going to apply this straight away to the first problem that we looked at, which was to do with the swimmers. So we're going to reduce the rows, first of all, by subtracting the minimum value from each element in that row. Now, they always want us to reduce the rows first. You could, in theory, reduce the columns first, but every single time they ask you to do the Hungarian algorithm, they say, by reducing the rows first, perform the Hungarian algorithm. So that's why we always do this one first. So let's actually think about what happens here. We're going to allocate each swimmer to a stroke using the Hungarian algorithm, and we will also work out the time it should take them in the race as a team. So the first step was to reduce the rows by subtracting the minimum value from each element in that row. Well, what this is really doing is calculating some relative times that we've got here. So for Adam, the smallest value is 25. So I'm going to subtract 25 from everything in this row. And I'm actually just going to write it out like numbers in a grid. I'm not going to write A, B, C, D along the side. We can actually just draw this as a matrix. So I'm just going to do a large part for a matrix, and I'm going to subtract 25 from all of these things to get relative times that we've got here. So it would be 10 for butterfly, 11 for backstroke, 11 for breaststroke, and then 0 for front crawl. So this is saying really that backstroke and breaststroke take 11 seconds longer than the front crawl, and butterfly takes 10 seconds longer than the front crawl. So I'm just going to go through these. 23 is the lowest for the next one, so I'll subtract 23 from everything. That's going to be an 8, a 12, and a 0. I'm going to subtract 26 from everything in the next row, so that is a 7, a 9, a 13, and a 0. And then I'm going to subtract 24 from everything because they're all fastest at the front crawl. So we're going to subtract 24. What's that going to be? 8, 14, 24, and 33. That's 9 that we've got. So this is our first matrix that we've got here. And in the mark schemes for AS, they always have them with the letters, but in A2, they just have them as matrices. So it's perfectly okay for us to do this as a matrix like this. That was us reducing the rows. The next thing I'm going to do is the next step, which is to reduce the columns by subtracting the minimum value from each element in that, oh, it shouldn't say row, it should say column. I'll make sure that's changed in the PDF. So we're going to subtract the minimum element in that column that we've got there. Okay, so looking at this one now, the minimum one is a 7. So I'm going to subtract 7 from all of these things that we've got. So it's going to go 3, 1, 0, 1. In the next column that we have, the minimum is an 8. So I'll subtract 8, which is going to be 3, 0, 1, and 6. The smallest is 9, so I'll subtract that and I get 2, 3, 4, and 0. And there's nothing to do here. There's already these zeros that we've got. So again, these are like calculating the relative costs sort of in the vertical sense. Okay, well, this is all of the backstrokes relative times to the front crawl. Now we're going to work out those times relative to each other. And then the next thing that we do is this part. We determine the minimum number of horizontal and vertical lines required to cover the zeros in the matrix. If this is n, you have an optimal solution. So I'm going to use one of my vertical lines like this. You can either do it with a pencil or whatever. That's one vertical line. I'm then going to do a horizontal line to cover that 0, a horizontal line to cover that 0, and a horizontal line to cover that 0. There is no other way that I can't use fewer than 4 lines that we've got here. So I've had to use 4 lines, so it is optimal. Now all I need to do is figure out which person does which thing, and you do that by having a look at where the zeros lie. So if there's a single 0 in a column, that one we have to assign. So that means I have to assign that one and that one and that one, and then because there's a 0 anywhere here, but there's actually only 1 0 in that row, so it has to be assigned in this particular way. And then we can just write down who gets assigned to do what thing. So looking at the original table that we've got, Adam is going to be with the front crawl. So I will say Adam, front crawl. And actually, I'm also going to jot down what that time is because that will save me something in a second. Boris is going to be doing the backstroke. And that is 31. Carl is going to be assigned butterfly. Which is 33. And then Dean will be assigned breaststroke. And that is 33. So then the total time is just those things added together. I'll just grab my calc. So that is a 25, a 31, a 33, and a 33. That is 122 seconds, or yeah, presumably that's seconds. It's not going to be 122 minutes. So that's their total time for this. And whenever you have those zeros, that's how you know that something has been allocated in the most efficient kind of way. So you might like to have tried at the beginning of this whole video to try and think, how would you allocate them yourself? The best allocation you can do for this is 122 seconds. So let's try another one of these, and then you can have a go on this next one that we've got. It says the table shows the times in minutes that each worker would take to perform a task at work. Allocate the tasks so that the time taken to do the set of tasks is as small as possible and work out the total time that it will take. Okay, so I'm going to begin by reducing the rows. That means I'm going to start by taking 80 away from all of these things. 250 take away 80 is 170. That's going to be a 0. 160 take away 80 is 80. I'm going to take away 90 from these, so I'll do 230 take away 90, which is 140. That's a 0. And 150 take away 90 is 60. I'll take away 110 from these, so that would be 120 and 30. And then the next thing I will do is I will reduce the columns. So I'll take 120 away from these things, which is going to give me 40, 20, 0. They all stay as a 0. And then I'll take away 30 from these, which is 50, 30, and 0. So now I'm going to see what is my next stage. I'm going to try and cover the zeros. So at this point, I'm going to cover this with the zeros and this with the zeros. So that is only 2 lines that has been covered. That means we're going to have to go and look at the next stage of this. So this is smaller than n. It was a 3 by 3, and 2 is obviously smaller than 3. So we're now going to find the smallest uncovered element, and we're going to call that E, and then we're going to augment the matrix by this. So in this particular case, our E that we have is the smallest of the uncovered, which is 20. So now we are going to augment by 20. Now remind ourselves of what this means. If it is covered twice, you add E. Covered once, you do nothing. If it is uncovered, you subtract E. Okay, so I'm actually going to get rid of these E's and replace them with 20s. And I always start off with the one that is the one that is covered twice. Okay, so the one that is covered twice, we're going to add 20. The ones that are uncovered, we're going to do nothing to them. The ones that are remaining, we take away 20. Okay, now that we've done that, it says repeat steps 3 to 5. So we're going to do that whole process of finding the minimum number of horizontal and vertical lines required to cover the zeros. And if it's 3, we've done it. So I definitely want to cover one like this, and I've got to do another one here. So this means that it's optimal. And then we just think about where we're going to assign these zeros. So there's only 1 0 in this row, so I'm going to definitely use that. There's only 1 0 in this column, so I'll definitely use that, which means that the last one I have to use is this one, so that you have 1 0 in each row and 1 0 in each column. So this means that A is going to do task 2, and when A does task 2, that's 80. It means that B is going to do task 1, which is 230. And it means that C is going to do task 3, which is 140. And so the time of those 3 added together, that's 80, 230, and 140, which is 450 that we've got here. And this is in minutes. So that's 450 minutes. Okay, I want you to have a go at this one. It's a lot bigger. We've got a 5 by 5 one. So I want you to pause the video and see if you come up with the same thing that I do for this one about some task allocation. Okay, so it says the table shows the times in minutes that each worker would take to perform a task at work. Reducing rows first, use the Hungarian algorithm to allocate the tasks so that the time taken to do the set of tasks is as small as possible, and work out the total time that it will take to complete the 5 tasks that we've got here. Okay, so this one is a lot more involved. It's going to take a bit longer. We're going to start off by reducing the rows. So I'm going to take 3 away from everything here. That's going to give me 6, 5, 0, 3, and 7. I'm then going to take away 5, so I get 0, 0, 2, 0, 0. I'll take away 3, 7, 6, 0, 6, 7. I'll take away 2, which gives me 8, 5, 0, 7, 5. And I'll take away 2, which is 7, 6, 0, 5, and 8. Okay, I'm now going to come down to here and I'm going to reduce the columns. So there's a 0 in here, so that's all going to subtract 0. There's a 0 in here, so that's all going to subtract 0. There's a 0 here, there's a 0 here. Actually, when I do that, nothing is going to change for that, is it? So this is actually, I've reduced the rows and none of the columns need reducing because the minimum value in each of them is a 0. And obviously, if you subtract 0 from all of them, they're going to stay exactly the same. So we don't need to show any more of that. This means I can just go about with the kind of lines. Now, the minimum number of lines, obviously you could go 1, 2 as the 3, 4, 5. That's a maximum way of doing it, but we're always trying to do the minimum. And the minimum is obviously 1, 2 that we have here. So let's have a look at our E that we have time. It's the smallest of the uncovered elements. So it looks like the smallest of these uncovered elements is 3 that we have here. So I'm going to begin saying this is where I'm going next. I'm going to begin by augmenting the matrix by 3, which means this will increase by 3. These will stay the same, and these are all going to decrease by 3. So I'll start off and replace that 2 with the 5, and then I'll have the 0, 0, 0, 0, 0, 0, 0, 0, and then everything else is going to decrease by 3. So it's going to be a 3, 2, 0, and a 4. A 4, a 3, a 3, and a 4. A 5, a 2, a 4, and a 2. A 4, a 3, a 2, and a 5. Okay, we'll do the same process of covering with zeros. So there is this, this, and this. Okay, so the next thing that we can see is it's still not optimal, but E is going to be 2 this time because that is our smallest uncovered. So we're going to go about this same process. Again, I like to start off with the ones that are double covered, which are going to just have E added to them. So the 5 and the 0 are going to have 2 added to them. So the 5 is going to become a 7, and that will be a 2. And then the ones on the yellow lines are going to stay the same. So that's a 0, a 0, 0, 0, a 0, 3, 4, 2, a 0, 0, and a 0. And then the rest all have E taken away. So they all have 2 taken away. So it's going to become a 1, a 0, and a 2. A 2, a 1, a 2, a 3, a 0, a 0, a 2, a 1, and a 3 that we have here. So let's try and cover the zeros. I'll cover that long line of zeros, this long line of zeros. I'll do this long line of zeros, and I have this long line of zeros here. So I've now got 1, 2, 3, 4 of those long lines of zeros. So let's keep going. This is now going to be my smallest uncovered value is a 1. So I'm going to augment the matrix now with 1. Remember, anything double covered, I'm going to add 1 onto it. Okay, so let's add 1 onto the double covered bit here and here and here. And then the other parts will stay the same. So that's 1, 0, 0, 2, 0, 0, 2, 0, a 0, and then a 3, 0, 4, 0, and a 0. And then the other ones are going to have 1 subtracted, so that's going to become 1, 0, 2, 1, 1, 0, 1, 2. Now I can cover these are all with a line. I'll have to cover this, this, this. No, there's a better way of me doing this, I think. I think I'm going to have to use 5 though. So I've got 1, 2, 3. Yeah, they have to be done with 5. Basically, it needs 5. Whichever way you draw it, you're going to need to have 5 here. So 5 lines. So optimal. This means I'm just going to have to figure out where the zeros are going to go. So look out for the places where there's only a single 0 in a row or a column. So there's a single 0 here. Is there another single 0 anywhere else? I think, let's have a look. There's also a single 0. Here there's a single 0 in this column. But then the rest, I think, can be kind of dished out in a different kind of way. So the ones that definitely need to go is that B needs to go with task 1. And if B goes with task 1, that is worth 5. And we're saying that A is going to go with task 4, which is 6. And then we just need to allocate C, D, and E in a way that works for these remaining ones, okay? So C, I guess I could put C here, D here. No, I couldn't actually. These two are going to have to switch. So C and E are going to have to go in either these places. So I can either do like this and this, which means that D would have to go in that place. Or I could have done it this way round, like this. So if you've got either of those answers where C and E are switched places, that's perfectly fine. I'll leave it with this version that I've got here, which is that C is going to go with task 3, D is going to go with task 5, and E is going to go with task 2. Now, if C goes with 3, that is worth 3. D goes with 5, that is worth 7. And if E goes with 2, that is worth 8. So the total, if I were to work that out, what have we got? We've got 6, 5, 3, 7, and 8. That's 29. Now, the alternative one that I said is we could have also said that C went with 2 and that E went with 3. Now, if C went with 2, then that was 9. And if E went with 3, that was 2. And notice how if these, the 3 and the 8 is 11, the 9 and the 2 is also 11. So there are 2 possible solutions here. So I'm going to say alternative solution is this. The alternative solution, you could have C and E. So this kind of allocation you have to do with a bit of like logic at the end with this stuff, but they both give that same minimum allocation of 29 minutes or 29, whatever it is we're talking about in this question. So now you can go and do lots of practice from exercise 2A. It is quite fiddly. I use a highlighter here, but you might like to use a pencil because you know you can rub out the pencil and see what's underneath. You don't get marks for any of the lines in the exam. The only thing you get the marks for are just literally what the matrices look like. And then you get the final mark for this allocation at the end here. You may see them in the mark schemes with the letters alongside here and along the top, like as a table. But when we get to the A2 papers, you'll see that's not required. So even if it's like that in like Solution Bank or anything like that, really they're just looking for matrices. And it saves a lot of time without having to constantly write out all of these letters each time. So go and have a go at exercise 2A, and I'll see you in the next video where we talk about something called dummy entries.